Okay, I'm just going to start off by dropping a few small hints, not huge ones, to help with the assignment. The calculation of the combustion of alcohol does cause a lot of confusion every year, and it is a sort of it's a bit of a testing ground for the grades, I suppose, really, as much as anything. It's not something you have to know very much about, but it's using just the bits of information that you're given, really. This is the merest sort of introduction to energetics, because from about the second week after Christmas we start the new unit, and we're straight into the energetics learning outcomes. So we go into this an awful lot more, and how to make measurements of these things, and then you'll do some measurements of temperature changes during chemical reactions and use those temperature changes to work out enthalpy changes. And this is just an introduction to because the reason I put this in is because when you're talking about alcohols particularly, and a lot of the organic compounds, to be honest, one of their main functions in everyday life is as fuels. And it's getting that energy out of those fuels, which is really important to us. So it seemed like a good opportunity just to divert and work out how much energy can you get out of these chemical bonds by breaking them and forming new ones. If you've got the balance right, you can get an awful lot of released energy. And so this is not a big deal. So don't feel you've got to go off and find out everything there is to know about enthalpy changes to do with this one. This is just a straightforward sort of follow the instructions with a twist. All right, so you can get a pass on this quite easily just by calculating the enthalpy change of combustion using bond enthalpies, but that really isn't all there is to it. Now, one of the key things, if we just go back to what we've gone through, one of the key things is to remember what sort of reaction it will be. It gives out heat, so it will be exothermic, and consequently the value you should get for the outcome should be negative. Yeah. So that's the first thing. So over on the right there, our exothermic one, our reactants, the ethanol and the oxygen, start with more energy than the products, which is the carbon dioxide and water. Make sure you've got a properly balanced equation for it. Don't forget state symbols. And that was where we were having trouble with the board, weren't we? Had to do a complete turn it off and on again. I was looking at that wondering what had happened. And we started looking at the notation for this, and remember that it's this one on the right here, delta H naught, with the naught, a 0, as a superscript, not an O, all right, not a big O, a little o, it's a 0, so it's the oval shape rather than a circle. That is probably what you'll use, unless anybody's managed to find the standard symbol, but delta H naught is fine. And this denotes standard conditions, but different sorts of enthalpy change have to be identified to make other sort of requirements, shall we say. So, for example, you've got delta H naught R, the standard enthalpy change of reaction. This one just occurs in the molar quantities in an equation. It does use standard conditions and reactants and products in standard states. That's going to be the same all the way through. But with this one, it doesn't matter how many moles of anything you've got. It's just the enthalpy change in that reaction. This one, the enthalpy change of combustion, this is the change when 1 mole of a substance is completely burned. Standard conditions and states, and this is the one that I've got to sort of divert off now. Formation down here, we'll leave that because we don't worry about that one. So the standard enthalpy change of combustion, which is the one you've been asked to do in the assignment, says standard conditions and states. All right, standard states. So you will need to have an equation that has standard states in it, state symbols. However, bond enthalpies, note at the beginning, only used in gaseous state. And that's where the conflict comes, because you can't then, strictly speaking, work out the enthalpy change of combustion, which is in standard states, using bond enthalpies because they're only in the gaseous state. You can, however, use some other enthalpy changes to make it work. All right. Now, the one that is particularly relevant here is the enthalpy change of enthalpy of vaporization, which is the conversion between liquid and vapor. All right. Now, if you put energy in, you will convert a liquid into a vapor. Energy will come out when a vapor condenses into a liquid. So you look at your equation and you work out whether you need to put some more energy in or let some more energy out. And I've given you values for enthalpy of vaporization for water and for ethanol. All right. Now, I'm not going to tell you quite what you've got to do. You do have to explain what's going on, but the answer should come out, I think, at minus 1099, if I remember rightly. All right. But that, you know, that won't get you a merit just writing that number. All right. It's the, you know, saying what's going on there. All right. So you don't have to have gone that far to pass it. Okay. But the, you know, explaining where those enthalpies might need to go in or come out might require a little bit of explanation. And so we did this example, ignoring that, the one on your assignment. This was the example we looked at. Involving the, what was it? This was the reaction between nitrogen and hydrogen. Looks like I hadn't quite finished it off, actually. I put N2 is an NN triple bond, H2 was an HH single bond, and then we've got N to H bonds. And those were the bond enthalpies that we find in those bonds. So the 945 represented the whole triple bond. That's not for each one of the 3 bonds in there. That's the whole triple bond. The 436 is the single bond between the 2 hydrogens. The 391 was the nitrogen to hydrogen single bond. And this was to calculate an enthalpy change of reaction for nitrogen and hydrogen reacting together to make ammonia. And it was a matter of putting energy in on the left-hand side to break the bonds, and then energy coming out on the right-hand side when the new bonds were formed. Now, you can confuse yourself by putting symbols in here, but you've got to bear in mind what they are representing. So it's sometimes best just to leave them as digits, not to put the signs in, or to put them in brackets, and then do the calculation as I've got it down here. So it's your energy on the left minus your energy on the right, which gives you the overall energy change for the complete reaction, and there it's minus 93 kilojoules per mole. So there is some heat coming out when nitrogen and hydrogen react together to make ammonia. All right, so that was where we left it. I did wonder whether we'd have time to do any more examples of those, but we don't really need to, because we're going to have an awful lot of them come up in the next unit. And I think, to be honest, that is enough for, you know, to give you the background for the assignment. That really only leaves you with one thing that we need to do for the assignment, but I'm going to leave that until after Christmas. All right, some of you will be thinking, oh, but I wanted to get that finished. You can read around it. You can read around the organic reaction mechanisms that I've given you on the end of the assignment. They are methane and bromine, a free radical substitution reaction, and ethene and hydrogen bromide, an electrophilic addition reaction. You'll find both of them in detail on ChemGuide. All right, but you won't necessarily understand curly arrows. Now, it's up to you. I mean, you know, if Christmas turns out to be, you know, really dull and there's nothing much on telly you want to watch, and you know, you've got a day to yourself and you want to read up on those, by all means do. And you can actually easily find out what curly arrows are and how they work. So I've said there, explain in detail using curly arrow diagrams to illustrate electron movements, the mechanisms involved in the reactions between. Okay, you will need to reference that bit because, yeah, the information is going to come from somewhere, and the chances are you will have to copy and paste the curly arrow diagrams that you're going to need. All right, so if you do want to get ahead, you can, but I'm going to practically teach those two examples anyway after Christmas. So, yeah, that's something you can just put aside for a bit, and then I think you've still got a couple of weeks to get it in after that. So what I was going to do today is to finish off some of the organic bits, and I've got a bit of a list, sort of wish list for today. The plan is going to look at carboxylic acids, partly because they are going to be important in biochemistry. We call them fatty acids in biology. And I don't know why, really. We can't call them carboxylic acids, but no, we still call them fatty acids, just to be awkward, I think. So we're going to look at general formulas, isomers, naming, go back to that bit of that, and then go back to the idea of reactions, actually a reaction between acids and alcohols. We call it ester formation or esterification, producing esters. Esters actually are some of the most common compounds in smells. We looked at the idea of organic smells, didn't we? And esters are, a lot of the fruity ones are esters. But ester bonds, a reaction between acid and alcohol, is going to be something we need when, again, in the biochemistry unit, when we get on to how fats form. So that's why I want to do these here. And then this afternoon, we will just have a very quick skim through a few bits, including unsaturated molecules. That's molecules that have double bonds in them, because you're going to need that for one of those reaction mechanisms, and how the double bond actually works. Then just a quick whiz through a few other groups, including some of the biochemical ones, and then there's a little fun practical to finish with. And we've timed it to perfection this year. It's a good one to do just before Christmas. Right, okay, carboxylic acids. Let's see how this goes. And these obviously are going to need a general formula, much like everything else. And I'll keep it simple to start with, but the general formula is rather like the alcohols, except that here we have CN, H2N plus 1, and then we have a bit that looks strange, but this is our functional group. And although with the alcohols it was just an OH group, here we've got another carbon involved. So we have C, and then it's written OOH. So that functional group there, it's called a carboxylic group or a carboxyl group. I prefer carboxyl actually, but that bit there, the COOH, carboxyl, I think is okay. So carboxyl group. We will come to that again when we're talking about amino acids in proteins. And I might call it carboxyl, I might call it carboxylic, I don't know. You never can be sure till I get there. But it's that makes it a carboxyl acid or carboxylic acid. Now, some of you might have heard carboxylic before, and it would go right back to your mitochondria assignment when you were looking at Krebs cycle, sometimes called the citric acid cycle, and sometimes called the tricarboxylic acid or TCA cycle. Tricarboxylic acids have 3 of those, but actually the cycle isn't made up of all those. Citric acid does, and I'll give you the formula for citric acid, and you can try and draw it. But we'll stick with these for now. So we have a curious situation here in terms of naming. if our number of, we can actually have n, our number of carbons here can be 0. So you see what I mean? Because we've got one already, we can actually have a 0 as our first one in this series. What formula would that give us if n was 0? It is odd. Any offers? It is, effectively, yes, it's just H, COOH. That is the first one in the series. So that one, what would the beginning of its name be? One carbon? Meth, yeah. It's methanoic acid. Now, that one, the old name for that was formic acid. And that comes from the Latin name for ants. That's it, yeah. Ants squirt acid out, and it's formic acid. Yeah, exactly. There you go. So, yeah, methanoic acid is otherwise known as formic. Right, so if n was 1, what formula do we come up with now then? This should be a bit easier. That's it. Yep, CH3, and then we've got to have our COOH. Some people will write that CO2H, but I'll show you why not, why I prefer not to in a bit. It's the structural setup for it. So if you had to guess what that was called, ethanoic, yeah. But this one, other name for this one? Acetic, which is, I tried to get this one out of you the day we were being observed. It's vinegar, yeah, ethanoic acid. You'll find, if you look on stuff that's flavoured, like salt and vinegar crisps, for example, it'll probably say ethanoic acid or acetic acid. It won't say vinegar, because they don't use vinegar, just use ethanoic acid, which is essentially the same thing. It's what you get if you allow alcohol. They start with alcohol and allow it just to keep going and going and going, and you end it with vinegar. Right, so we could keep going, but let's just do another one or two. So the next one would be C2H5COOH, and we shall call this one not pent, no, that's prop, yeah, that's right, you knew it began with P. This one's propanoic. And so it goes on. We could do loads of them. At this point, I'll sidetrack and give you the formula for, or the name for, citric acid. Just as a sidetrack, citric acid is, I should give you something to write this on, or draw it on. It is 2-hydroxy propan one, two, three. I've run out of space. Tricarboxylic acid. Okay, have a go at drawing that in pencil. Or if you don't really want to, we don't want to bother getting the mini whiteboards out at the moment, but have a go between you if necessary. Right, 2-hydroxy propan 1,2,3 tricarboxylic acid. So what's the bit that tells us which acid we're using? How many carbons? It's the propan, yeah? That's why I've stopped at that point where we've got a propanoic up there. What's hydroxy? It's two atoms. It's hydrogen and oxygen. Yeah, so it's an OH group, that's all. So propan is telling us how many carbons altogether? 3? Yeah, okay. Let's so 1, 2, 3 would be our start. 2-hydroxy is telling us, no, that would be dihydroxy. 1 OH on the second carbon, yeah. So let's stick it there. And then it's telling us we've got 1, 2, 3 tricarboxylic acid. Oh, this is going to get messy. So we've got to turn each of the carbons into a COOH group. I think. I don't think we have to put another C on. Wouldn't work because you'd end up with, yeah. I think it goes. I'll have to find a diagram of it now just to check. Now I've set the seed of insecurity. An OOH group on here would go, we do a double bond to the O and then OH. So there's one. Oh, that's not going to work on there. Oh dear. If I can do it on there. If I can't do it on there, okay. I must be wrong. That is a phrase you will not hear very often. Right. It must be that they've got... Oh, I looked it up on Wikipedia as well. Yeah?
It is the extra carbon as well.
As well, on all of them? Extra carbons on all of them. Right, okay. Yeah. Okay. That's a little bit odd, though, because that will make our chain longer. Just going to have a quick look for... Actually, I'm going... Let's be absolutely accurate on this. I'm going to steal a diagram. Citric acid. We can buy some. Oops, no. Oh, look, there it is. Okay. Let's select that. I don't want to copy it. It's going to get a bit big, isn't it? Way, right. Right. I'm going to put the carbons in just to make it a little bit easier for us. Here, this must be our carbon 2, mustn't it? Oh, slipped, hasn't it? So, yes, we've got... All right. Those are our 3 carbons that I started with up there. Then it all went horribly wrong, didn't it? See, so, yeah, we've got another carbon there, there, and there. Oh, I'm so glad I chose that as an example. Yeah, sometimes, yes. So we've definitely got a C, O, OH on there, a C, O, OH on there, and a C, O, OH on there. I've just drawn mine the other way up. I had my OH going up, whereas it's down on this one. Yay! Well, that was a good idea, wasn't it? You get the idea. I mean, these skeleton diagrams are so helpful sometimes when you've got a huge molecule like that. I mean, there should be some H's coming off here as well, but you just always assume that if you've got always your carbon's got to have 4 bonds. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. There's something missing. What did I do? I'm missing a C, yeah. I still can't get it right. COOH. Oh, there we go. And I've joined it up and it's a real mess. People sometimes ask, why is this written HO rather than OH? And it's because the O is the bit that's attached to the carbon. So you have to write it that way round. One of the molecules on your assignment is, I hope you found it fairly easy to draw, propane 123 triol. Yeah. That's actually, I'll draw it for you because I want to draw it a particular way. You can draw it one of two ways. Are you all finding drawing software that's helping you with this? I keep trying on here, but it just won't for some reason. The propane 123 trial, just as a complete sidetrack. Your propane is your 3 carbons, 1, 2, 3. So you put an OH group on all of them. Now, just depending on how you draw it, of course, if you stick them out this side, you'd be like that. And then hydrogens all the way round. Alternatively, you can make it Christmassy. And that's why I have to do this. Because we go. Ho, ho, ho. So it doesn't matter which way it goes. You could alternate them if you wanted to. I mean, it's no different because those bonds rotate anyway. So if you don't find the drawing software, then you either have to just steal one off the internet or use just the ordinary drawing tools in Word. Can do it. Lines, letters, that sort of thing works. Be a bit of a challenge, but yeah, I should take that off now, shouldn't I? Really, because I shouldn't be giving away answers. Pointless exercise that is, because it's all recorded, isn't it? But it's in the wrong place, so that's why I don't want that there, because this is the carboxylic acids bit. All right, so the rules are basically the same as with everything, and in terms of naming isomers, you can do the same sort of thing. I mean, that has already shown us how we might do, with 3 carboxyl groups on 1, 2, and 3. Well, you could take any example, and we're not going to spend ages on this because I want to talk a little bit about the reactions. But naming isomers, just as before, it would be using the numbers as, as any other example that we've used with the alcohols, with the alkanes, all of those things. So we might have, if you took, let's take a slightly longer, let's say pentanoic acid. I shall probably wish I hadn't chosen that one. How many isomers of pentanoic acid could we make? That's probably going to be quite challenging. There you go, have a go. See if you can make me an isomer of pentanoic acid. Actually, I'm going to start you off with the obvious one. 1, 2, 3, 4, 5, and then we would have our O and OH. I'm not going to draw in all the hydrogens, we just make the assumption that they're there. What would we actually call that one? This is where you've got to think, we want to say that the carboxylic group is on the first carbon. So somewhere we need a number 1 in there. Where are we going to put it? Sorry? Yeah, pentan 1-oic acid. It's a bit clumsy, but you know, theoretically that is how you do it. So this would be pentan 1 oic. So you should be able to then work out other options. We do have, I don't know whether we can actually put it on any of the other, can we put it on the others? No, we end up having to use complicated names like that, don't we? Because the problem you've got is, I hadn't actually thought about this before I got to this point, as it's fairly obvious. We've got 3 bonds that we've got to use up in the O and the OH. So, in fact, we can't join that group onto any of the others, can we? I didn't even think about this, clearly. Blindingly obvious, isn't it? You can tell it's the last week of time. But if I tried to take my 5 sulfate, yeah. Nitric acid would give you nitrates, yeah. With this one, ethanoic acid gives you ethanoate, which, you know, old names would be acetate. Right, this is going to give us ethanoate. And similarly, you know, you'd get methanoate from methanoic acid, propanoate from propanoic acid, and so on. So we've got ethanoic acid and propanol will give us, what shall we call this ester? Something ethanoate. So, we're getting close. Methanol would give you methyl, ethanol would give you ethyl. This is propyl, right? I'm not sure if it's, I think it's propyl, not propanyl, because it's not methanol. So it's propyl ethanoate. That's water. Now, the really odd thing about this is actually that when you write the formula out, it's actually written with the second name first, or the acid part first. I'm going to use colour just to make it clear. And I chose two different ones. I didn't choose ethanoic acid and ethanol for this reason. I'm beginning to wish I'd chosen methanol because it's easier to draw. But ethanoic acid would be, let's do it in its simplest form. Not be that, would it? Right. So that's our ethanoic acid. And I'll do the propanol, which is C3H. Asking too much at the moment. The bits that we use to make water here are going to be the hydrogen of the acid and the OH of the propanol. So what we end up with is actually written back to front because we want to put the propyl group instead of the hydrogen. So it goes CH3COO, and then we put in the C3H8. And I can't really do colour for the H2O. So H2O is just the rest of it. Okay, now I've introduced these because they turn up in, I think the second learning outcome of the new chemistry unit, energetics, kinetics and redox. The kinetics bit is about rates of reaction, and there's a couple of examples that use esterification reactions, so it was just worth writing an example out. But as I say, similarly you get esterification in biochemistry, and that propan 123 trial that you've got in your assignment is also known as glycerol. And glycerol is the backbone of fat molecules, lipids, and you get 3 fatty acids reacting with the 3 OH groups, and we get 3 ester bonds forming. So you know that's where this will be relevant, really. The other reactions I will just summarise that you've got the same. Board slightly out of line again. So it would be the same, that you would have acid plus metal would give you a salt and hydrogen. And if you replace that propanol that I've got up there, let's say with magnesium, it would work out the same way. All right, that you'd put the magnesium after the name of the acid, although that's a bad example because the acetate ion has only a 1 minus. So you need 2 of them. But sodium, for example, let's say we had ethanoic acid plus sodium, you would get sodium ethanoate, which would be CH3, COO, and then Na. You could have acid plus a carbonate. So you could react it with calcium carbonate, sodium carbonate, it doesn't matter, but you would still get the same sort of salt production, but you'd get carbon dioxide and you'd get water. And then, of course, you know, you could have a carboxylic acid with a base. It doesn't have to be an alcohol. You could similarly react it with copper oxide or potassium hydroxide, and you would get the same effect as we have had with the inorganic one. So acid plus base gives salt plus water. And these are known as salts. These are not esters. An ester is only what you get when you react together a carboxylic acid with an alcohol. I think when we haven't done any other acid reactions. Organic carboxylic acid ions, you will also find them in the blood and body fluids. Obvious reasons, you know, they are components of organic sort of life compounds. And I think it's, I try to think whether it's, I think it might be the ethanoate ions are involved in nerve impulses, I think. I never include them, and I don't include any other negative ions either. We only ever talk about sodium, potassium, and calcium at synapses. All right, let's just tidy this little bit off by thinking about, I should have left this open, about the smells thing again. And if I put ester smells table, that sounds really odd, but I think it will know what I want. Yeah, there they are. We did look at a big one of these, didn't we, that looked at a whole lot of organic compounds. I only want the esters. All right, that's going to be a, is this just esters? Let's see if I can stick that into here. I think I might need a new page for that. Yeah, optimize. Okay. What can we see? It gives you the first name across the top and then the second name down the side. So you've got methyl methanoate. I have no idea what ethereal means in terms of a smell. Heavenly, don't know. But then you've got some very definite ones. Methyl ethanoate, glue stick. Methyl propanoate, fruity. 2-methyl propanoate, fruity. Methyl butanoate, very definitely pineapple. Methyl pentanoate, flowers. Coming down, methyl benzenoate. We haven't mentioned benzene yet. I think that's vanilla. Looks like a starfish. Oh, oh, yeah, not sure. Methyl heptanoate, very definitely berries. Methyl octanoate, oranges. Methyl nonanoate, no, that's not a pineapple, it's a coconut. Coconut and alcohol. So that's sort of suggests a bit like, I was going to say Malibu. So it goes on. So you've actually, you know, these are not, I mean, these are some more diverse ones as well down here. But you can see there's a real preponderance of fruits on there. I think those leaves are probably mint. So, you know, this is, when it comes to flavourings in foods, this is how they go about it. Now, you know, people think, oh, yeah, it's got artificial flavourings in. Well, what's the difference between an artificial flavouring that's made in a factory and the exact same chemical that comes out of a plant? Very often, nothing. And they call them nature identical, is how they're described. And a lot of flavourings are actually just produced in a lab in a concentrated form, but they are the exact same chemical that you would extract from an apple, a pineapple, a pear, a banana, you know. So they're and flavourings, I think, have improved an awful lot over the years. There are some I still don't like because I don't think they're identical enough. I don't like strawberry flavoured things, and I don't like banana flavoured things particularly. But others, I think, are really sort of.
They use a banana species that has been extinct for like 50 years.
Oh right, yeah. Oh right. So the banana, yeah, the bananas. Yeah, I mean, they do change over the years. So yes, I think what we expect, and it'll just be balance of compounds and things like that that will change as you get varieties changing. Then yeah, and then sometimes they'll make them stronger in certain aspects than perhaps we used to. But yeah, there's, you know, they're very, very definite. So, for example, you know, if you want a nature identical cherry flavour, then up here you've got 2-methyl propyl ethanoate, and that will give you cherry flavour, and so it goes on. But this is, you know, this is one of the really distinctive things about esters, is their flavours and smells. The one I can't quite see what it's. Oh, PVA glue. Ethyl ethanoate. There is PVA glue. I always thought that was the one that was pear drops, but that's not right, is it? PVA glue doesn't smell of pear drops. If you know what I mean by pear drops, old-fashioned sweets. But yeah, maybe that's the pears that are next to it then. Propyl ethanoate. Yeah, who knows? I'm not entirely sure what these are over here. Heptile ones, like lumps of wood, don't they? Anyway, yeah, you could stare at these for ages, couldn't you? Oh, fancy that. There's a lot of alcoholic ones down at the bottom there. Rows of bottles across here, look, and further down there's you know, quite distinctive sort of alcohol flavours. There's a few other odd ones, like we've got some sort of fungus over there, and a parsnip. Parsnip.
Above it, the red stick.
Above the parsnip?
Yeah.
I think that's a candle. Yeah. So, yeah, candle, we've got, what's that one? Octyl 2-methyl propanoate. Okay.
Is that like a smell of the candle?
I think, yeah, just the smell of wax, as it were, sort of, yeah. But then, yeah, I mean, you can get fruity candles as well, so you'd have to mix some of these others in with it, wouldn't you? Apple. Oh, what, this one? Yeah, I think that's one of those very specific bottles of. It's not Disaronno, not that one. That's square, isn't it? But are those sort of ones? Or yeah, brandies, that sort of thing. Yeah, that sort of thing. I think. I don't know whether. That'd be a bit of a specific smell. Oh, this ester smells of loot. Yeah. Okay. Well, there's one very obvious. I mean, we've got Bacardi up there at the top. It's got a very distinctive smell, obviously.
There's Jack Daniels on the bottom.
Oh, is that? Oh, we got, yeah. Yeah, we've got some interesting combinations. There's an interesting one over the side here. A smiley, some coconut, and a candle. So a happy coconut candle.
What's that underneath the candle?
What, that candle? Oh, the other, that candle?
Oh, yeah, what's that?
That's a parsnip.
Oh,
Right. I think that's probably a good place to stop for now, and you know, go off and sniff your lunch. And we will, yes, I'll stop recording at this point, and I'm going to start putting these on to YouTube using the same identifier as I've got for the two podcasts, and that will be ECCASH. All right, so ECC for East Coast College, ASH for Access Science and Health. Just to make it easier if you're searching on there, because I'm leaving them public, and I don't actually want other people particularly to be able to, I don't want them to be properly public, and I can't be bothered to set up subscriptions, so that they're targeting you particularly. But if you, I'm going to start attaching ECCASH to them, so that they're much less likely to be found. And then I might put the subject or the unit. So this might say ECCASH BROC, BROC, because that's bonding reactions, organic chemistry, and then 17th December. And then nobody else is going to find it, are they? Yeah, that's the worry, isn't it? I'll forget what I did as well, but it's all recorded, so as long as I can find the recording, I'll be able to go back and remind myself. Okay, we will stop at that point and I'll restart it this afternoon, or I'll start a new one this afternoon.